Good afternoon, everyone. We have a binomial expansion problem to do today from IB Maths Higher Level. This is a super interesting, challenging problem, probably one of the hardest binomial expansion problems, so it's a good litmus test for whether or not you understand the topic. And there's a lot of stuff here that's pretty intimidating. We've got two binomial expansions to do. They're multiplied together, and we've got a lot of things that we don't know. We're missing P, we're missing Q, uh, so there's a lot of intimidation at the beginning about a problem like this. But if you work through it with the correct strategies, you can do it without spending too much time on it, without taking too much effort, and without having to stress too much about whether or not you've got the answer right. So let's just give the problem a read. It says, given that 1 plus x to the power of 3 times 1 plus px to the power of 4 is equal to 1 plus qx plus 93x squared, and then a bunch of dots, and then p to the power of 4, x to the power of 7. So I think it's important to focus on what's actually going to be helpful here for us, because that can cut down a lot on the amount of work we have to do. A lot of these expansions are going to go to some high powers, right? We're going to have an x to the power of 3 out of this. We're going to have an x to the power of 4 out of this. But really the highest terms that we're interested in is the x squared. So there's no reason for me to go beyond the x squared in either of these expansions. And actually, there's a lot of information here that's not as helpful as it first seems. For example, the 1 at the beginning just comes from multiplying out the 1s. So that's not giving me any helpful information. And the p to the power of 4, x to the power of 7 at the end, again, that's just going to be the final term, but it's going to be exactly the final term that you get from multiplying this out. Because your last terms are going to be p to the power of 4, x to the power of 4, and x to the power of 3. You multiply those together. That's not meant to be subtraction, it's just far apart. You multiply them together, and you get p to the power of 4, x to the power of 7. So that's not at all surprising, and it's no new information. The two terms I actually care about are these in the middle, the qx and the 93x squared. So we just need to optimize really for finding the parts of our expansions that are going to give us a qx and a 93x squared. So we only need to go up to the squared terms. The first expansion, I suggest we just do these. The first expansion is actually fairly straightforward, right? It's 1 plus x to the power of 3. If you're familiar with Pascal's triangle, you can do this fairly quickly, right? 1, 2, 1 is for when we have an expansion that's squared. 1, 3, 3, 1, those are going to be our binomial coefficients when we're expanding to the power of 3. And this just becomes x to the power of 3 plus x squared. I should go the other way, actually, shouldn't I? 1 to the power of 3, which is 1, plus 3x plus 3x squared. And then there's going to be a final term, which would be x to the power of 4, but I do not care about that term. So it's just the 1 plus the 3x plus the 3x squared. We're done super quickly with the first expansion. The second expansion I actually think is not that much more difficult. So there's a big intimidation factor here, but actually as individual expansions, these are not that bad. We're to the power of 4 here, so we'd be another line on our Pascal triangle. We're at 1, 4, 6, 4, 1. You get these numbers by adding them together, by the way. If you're unfamiliar, it's good really to, when you've got lower power binomial expansions, so squared to the power of 3 to the power of 4, having the first couple just memorized so you don't have to do binomial coefficients in your calculator is extremely helpful. You can write them out like this as well, that's fine. But the more intuitive or the more used to these that you are, the faster you're going to be able to go. So our first term is just 1. Our second term, we're going to have 1 to the power of 3. I don't care about that. It's just going to be 1. I do care about the fact that we now have a px, and we're going to have 4 px. So how are we getting these? It's our binomial coefficient, which is 4 from the Pascal triangle. It's 1 to the power of 3, and it's px to the power of 1. So this might take a little bit longer, or you might want to take your time if you're less familiar with these. But this is the sort of binomial expansion you really want to work up to a point where you can do these pretty fast and very accurately. So the next one, we're going to have a coefficient of 6. The 1 will be to the power of 2. I don't care about that. The px will be squared. That's more interesting. P squared x squared. And then there'll be more terms, but we've already established I don't care. Right? We don't need those additional terms. What we have then is basically these two expansions multiplied together. So we're going to have 1 plus 3x plus 3x squared times 1 plus 4px plus 6p squared x squared, and then again, . So these are two expansions that are now multiplied together in the way that you might multiply, factors in a quadratic or something like that. So where does our qx come from? Well, every single number in each of these expansions, when we multiply them out, is going to multiply by every other number in the expansions. But I don't care about every combination. I just care about the ones that are going to give me an x term. So if we start with 1, what can I multiply 1 by from the other expansion to get an x? Well, that's going to be 4px. And that's that. 3x, I can multiply by 1. And if I go any further than this, I'm going to have a square. So I actually just need those two components. I just need 4px and 3x. And those added together should give me what they're providing to me in the expansion, which is qx. And if I cancel out the q's, I get 4p plus 3 equals q. Nice and easy. So actually, the expansions themselves are not too difficult. If we think through how these are going to multiply together, we can get individual terms, and we get out of this one equation that relates p and q to each other. But one equation with two variables is not enough to know those values, so we need to get another equation somehow. And this is where my 93x squared term is going to come in. So I'm looking at what can I multiply different terms by in order to get an x squared. So if we start with our 1, which is here, I can multiply that by 6p squared x squared to get a term. So just pick 6p squared x squared times 1. That's an x squared term. 3, I can multiply by 4px. That's going to give me 12px squared. And then the next one is 3x squared times 1. That should just give me 3x squared. So these are the three parts of my multiplication that all have an x squared in them. And when they add together, they should give me the term in my expansion here, 93x squared. So let's try and work through and simplify this. 6p squared, 12p, 3, 93. Now this, I'm just getting by cancelling all of the x's, basically. All the x squareds are going away. We're left with 6p squared, 12p, plus 3 equals 93, which is a quadratic. I can solve this a bunch of different ways. I'm going to divide by 3 first, though, because it looks like everything will divide by 3. So that's going to be 2p squared, 4p, plus 1 equals 31. And then if we subtract that, 30 from the end, see, we have more space, 2p squared plus 4p minus 30 equals 0. Now everything's even again, so I'm going to go again. P squared plus 2p minus 15 equals 0. And that's a much less scary quadratic than we had at the beginning. So always with these, we're getting everything on one side, and I'm just factoring values out because it looks like it's working well. We're looking then, if we want to solve this by factoring, this is non-calc, so you do have to do this by hand. You could use the quadratic formula. I think the factoring here shouldn't be too difficult. We're looking for numbers that multiply together to minus 15 and add up to 2. So for me, minus 5 and 3 will work. So p minus 5, p plus 3 equals 0. And we get here two different values for p. P equals 5, p equals minus 3. And that comes from the fact that we can assume in order for those two things to multiply together, they must both equal 0, or at some, one of them has to be equal to 0 in order for the multiplication to make 0. So if p minus 5 equals 0, p plus 3 equals 0, and that's how we're getting the p equals 5, p equals 3. two values then for p, which means probably there's a pair of values for p and for 5. And we were not told at the beginning that there was any restriction on p being positive. I just always go back and check at this point because I've definitely not remembered. But no, there doesn't seem to be anything here that tells me I can't have a negative p. So we're going to have to find solutions when p is 5. That's going to be 4 times 5 plus 3 equals q. 20 plus 3 equals q. So 20 plus 3 equals q. 4 times 5. P should be, oh, hang on. Just double check this. Minus 30. 2p minus 30. That makes sense. Divide everything. It's p squared plus 2p minus 5. Oh, I've done that completely the wrong way around. That's quite embarrassing. So this should be negative 3, positive 5. There you go. Good catch. I saved myself. So p plus 5, p minus 3 equals 0. So p is 3 or p is minus 5. Minus 5 goes in here. Then we've got minus 20 plus 3, so this is minus 17 will be our value for p. So that's one set of solutions. And then the next set we're going to have is p equals positive 3. 4 times 3 plus 3 is q. So this is going to be 12 plus 3, which is equal to q. 15 equals q. So two sets of solutions. When p is negative 5, q is negative 17. When p is 3, q is 15. So, I mean, there is a lot going on here, and it's made worse because you have to do this all without a calculator. But lots of the individual components I don't think are as scary as they seem at the beginning. You just need to do what are, by higher level standards, not too complicated expansions. And then you multiply them together and you've got to work out all of these components. But if you take it piece by piece and you just do what's immediately in front of you, it's a lot less worse than it originally seemed.